Assalamualaikum warahmatullahi wabarakatuh. Our group will be presenting topic 4, which is couple oscillation. When is couple oscillation happen? Couple oscillation occur when two or more oscillating systems are connected in such a manner as to allow motion energy to be exchanged between them. Between two oscillators share a common component, capacitance or stiffness, inductance or mass or resistance. In this topic, we will cover 5 subtopics, which is first, stiffness coupled oscillator. Second, 3 important parameters of coupled oscillator. Third, matrices. 4, coupled oscillation of loaded spring. And lastly, the wave equation. Stiffness coupled oscillator. Figure shows that two identical pendulums, each having a mass m suspended on a light rigid rho L. The masses are connected by a light spring stiffness S, whose the natural length is equal to the distance between these two masses at equilibrium. The equation of motion for x and y is described as m double dot x is equal to negative mg x over L minus s bracket x minus y. And for y, m double dot y is equal to negative mg y over L plus s bracket x minus y. In this motion, if x is bigger than y, the spring is extended beyond its normal length. For the equation, writing that omega naught squared is equal to gl, then x double dot plus omega naught squared x is equal to negative s over m bracket x minus y, which shows that spring is stretched. Next, y double dot plus omega naught squared y is equal to negative s over m bracket y minus x, shows that spring is compressed. As we did not solve x and y directly, we will choose two new coordinates, which is capital X will stand for x plus y and capital Y for x minus y. Adding equation 1 and 2 will give that capital X double dot plus omega naught squared x is equal to 0, and subtract this equation 2 from 1 will give that capital Y double dot plus bracket omega naught squared plus 2s over m close bracket y is equal to 0. Under two conditions. First condition, if capital Y is equal to 0, then x is equal to y at all time. So the motion is described as capital X double dot plus omega naught squared x is equal to 0. As shown in the figure, the pendulum will swing in phase and the stiffness of the coupling has no effect. And the next condition, capital X is equal to 0, then x is equal to negative y at all time, so that the motion is described as capital Y double dot plus bracket omega naught squared plus 2s over m close bracket y is equal to 0. And the figure shows that pendulums will always move out of phase, and spring is either extended or compressed, and coupling is effective.
So now I will continue with the second subtopic in couple oscillation, which is 3 important parameters of couple oscillation. So for the first one is normal modes of vibration. Normal modes of vibration is illustrated by the significance of choosing x and y to describe the motion, and they are also represented by the motion equations or normal modes for x component and y component. So basically, a vibration involving only one dependent variable, we call them a normal mode of vibration. So for the second one is normal coordinates. Normal coordinates is the coordinates of normal modes. So normal coordinates are the coordinates in which the equation of motion takes the form of a set of a linear differential equation with constant coefficient, in which in each equation only has one dependent variable. So for the third one is degree of freedom. Degree of freedom are the independent way of how normal modes acquire energy, and the number of degree of freedom will be the same as the number of the normal coordinates. So as you can see in this table, these are the example of normal modes. So as you can see, the first equation has omega naught as its frequency, and the frequency for the second equation are omega naught square plus 2s over m. So this equation characterized by the fact that all of its components oscillate with the same frequency, and this frequency we call them normal frequency or eigenfrequencies. So the complete equation or the general equation is given by the addition or superposition, as you can see in the table beside it. So the important properties for normal modes are they are entirely independent of each other and their energy is never exchanged with another mode. So after assumptions, the total energy of this normal mode may therefore be written as E component x equal to ax dot square plus bx square, while the E for component y equal to cy dot square plus dy square. So this energy is consistent with the total energy E equal to 1 over 2 mx dot square plus sx square. So the system of two coupled pendulums has 4 degrees of freedom. So the pendulum displacements are then given by x equal to 1 over 2 capital X plus y equal to a cos omega 1t plus a cos omega 2t. And for the component y equal to 1 over 2 capital X minus y equal to a cos omega 1t minus a cos omega 2t. And the velocity that given are x dot equal to negative a omega 1 sine omega 1 t minus a omega 2 sine omega 2 t, and for the component y dot equal to negative omega 1 sine omega 1 t plus a omega 2 sine omega 2 t. So this figure shows a system of the coupled oscillations, and as you can see, it is a combination of the in-phase mode and the out-phase mode. So in this system, the initial displacement x equal to 2a, y equal to 0, and it is at t equal to 0. And in phase mode, we assume it is a capital X, and the out phase mode as capital Y. So after release, the motion at the right hand side of the pendulum will be given by 2a cos bracket omega 2 minus omega 1 t over 2 cos omega 1 plus omega 2 over 2 t. So as for the left hand side will be given as 2a sine omega 2 minus omega 1 t over 2 sine omega 1 plus omega 2 t over 2. So to reinforce the importance of normal modes and its coordinates, let's review the equation that I have given to you before, right? This, the normal modes equation, and we modify the normal coordinates to read them as capital XQ equal to m over 2 square root x plus y, and the y and the capital YQ equals to m over 2 square root x minus y. So we can substitute these coordinates into the kinetic energy, potential energy, and total energy.
Now I'm going to continue the next subtopic, which is the general method for finding normal mode frequencies, matrices, eigenvectors, and eigenvalues. So in this subtopic, we can know the method to find the normal modes frequencies by using the matrix form, and also we will get the eigenvalues from the eigenvectors. Basically, when a coupled system oscillates in a single normal mode, each component of the system will vibrate with frequency of that particular mode. Thus, the metric method is adopted, as this method always yields the values of the normal mode frequencies and the relative amplitudes of the individual oscillators. So, as our coupled system in our case oscillates in only one of its normal modes of frequency, then the equation of motion would be mx double dot plus mg in bracket x over L plus s in bracket x minus y equal to 0. And another one, my double dot plus mg in bracket y over L minus s in bracket x minus y equals to 0. So let we consider these two equations as formula 1. The coupled system for an example pendulums start at rest, we can assume the solutions
are x equal to a times exponential I omega t, and also y equal to b times exponential I omega t, where a and b are the displacement amplitudes of x and y at the frequency. So we can take these two equations as formula 2. So we can derive the new equation of motion by inserting formula 2 in formula 1. So the formula will become like this. Now, at this point, we can find out the normal mode of system. When we sum up the new equations of motion, the expression will give in bracket a plus b times in bracket negative m omega squared plus mg over l equals to 0, which is satisfied when omega squared equals to g over l as the first normal mode. Whereas, if we subtract the expression will give in bracket a minus b times in bracket negative m omega squared plus mg over l plus 2s equals to 0, which is satisfied when the second normal mode, which is omega squared equal to g over l plus 2 times s over m. Next, we insert the value omega squared equal to g over l in the pair of equations. We'll keep a equals to b as the in-phase condition, but then if we inserting omega squared equal to g over l plus 2 times s over m, resulting a equals to negative b, which is the anti-phase condition. Dividing the equations by m times exponential I omega t, the equations will be like this. From this form of equation, we can take it to the form of matrix like this, where omega naught squared is equal to g over l and omega s squared is equal to s over m. So here, from this form of matrix, the column vector with component a and b is an eigenvectors of the matrix. Thus, if we solve for its solution, we can get the value of omega squared, which is non-zero solutions called eigenvalues. Also, the matrix may be written as alternative form like this. These equations have a non-zero solution if and only if the determinant of the matrix is 0, such as omega naught squared plus omega s squared minus omega squared overall squared minus omega s, the power of 4 is equal to 0, or we can write it like omega naught squared plus omega s squared minus omega squared is equal to plus minus omega s squared. Each normal mode frequency has its own particular value of the phase constant. The number of adjustable constant then allows the solution to satisfy the arbitrary values of the initial displacement and velocities of the system.
In this subtopic, we're going to learn on how a large number of particles are coupled together. And if attach n number of mass to a string, then how many normal modes will produce, what the frequency of normal mode, the displacement of each mass in a particular normal mode, and the amplitude. So that what we're going to know in this. So let's look at the figure here, where there is a mass that connected to a string which has a constant tension on the string and separated by the length of A. Okay, so we consider that the mass will only move upward and downward, which is we're just going to consider the y vertical displacement. So, and also noted that the end of the string is fixed. Okay, so the length of the string is equal to n plus 1 times A. And then we consider the equation of motion. Okay, the equation of motion of this mass may be written by considering the components of the tension directed toward the equilibrium position. So the equilibrium position is on the bottom one, the bottom line. So we're going to take that t sine theta 1 and t times sine theta 2 into the equation of motion. So also remember that in this figure, the theta is very small. So that when the theta is small, we can consider that sine theta equal to tangent theta. So that is why we can have that sine theta 1 and sine theta 2 there. Substitutes all the sine theta 1 and sine theta 2 into the equation of motion. Then we got the equation 1. After that, we know that this is a simple harmonic oscillating with the frequency. So we can assume the solution as what we stated there. There is 3 solutions there. And we can substitute all the above solutions into the equation 1 that we have derived from the equation of motion. So what we get from that is we got the fundamental equation, which is we're going to use the fundamental equation in this part. Okay, so always remember that the end of the string is fixed. So like look at the figure there. When I draw that the fixed end, the first fixed end equal to y naught, and also the last fixed end equal to yn plus 1. So when it is fixed, it means that there is no amplitude there, so the amplitude should be 0. So y naught equal to a naught equal to 0, and also yn plus 1 equal to an plus 1 equal to 0. Okay, by using the fundamental equation just now, I will substitute the R1, R2 until the Rn. R is the index of the mass, so that's why I said that in this couplet oscillation system of a ladder string, we consider that there will be so many mass coupled together, so that's why we focusing on the n particles. So just like for example, when R is equal to 1, so what's the equation I get is 2 minus ma angular frequency to the power of 2 divided by t and multiplied by a1 minus a2 equal to 0. Why there is no a not there, but in the fundamental equations there is, but because of that a not equal to 0 as it is the fixed end, and also same goes to the R2, and also same goes to the R equal to n. Okay, so also always remember that number of moles equal to number of mass. If we have such a very small or not so many number n's, so for example I got n equal to 1, so we just can easily get the angular frequency for n equal to 1. I will just use r equal to 1, so use the equation that we have derived, r equal to 1, and so that we substitute that into the equations, and what we get is angular frequency equal to 2t minus ma. So this is the angular frequency for n equal to 1, and for n equal to 2 we're going to use r1 and also r2. So we substitute that n equal to 2 into the equation that we derived for r1 and r2, and we eliminate a1 and a2 there, so we're going to get the angular frequency with the t divided by ma, also the 3t divided by ma. So there's the angular frequency there. So on the first part there, for n equal to 1, we know that only one mode of vibration, so the mass there is in phase. And for the second one, n is equal to 2, it is for the first one t, for the first angular frequency, which is t divided by a, we get a1 equal to a2, so it is in phase. So for the second one, the 3t minus m divided by ma, we get a1 equal to a minus a equal to negative a2, so it is out phase. That is when we want to find the general solution for any value of n. So we always going to use our fundamental equation, which has been stated there in the screen. Okay, but here we're going to modify a little bit by substitute the natural frequency into the fundamental equation. So that's how we get the second one equations, which is also be stated there in the pink box there. Okay, so by assume that AR equal to CE to the power of IR theta, which there C is constant, so actually we can get the general frequency formula and also the general formula for amplitude as shown in the yellow box there. But how do we can actually get both general formula? Okay, so we can see from the right hand side there
the wave equation. Equation of motion of the Earth's mass, which R can be any number, is second derivative of yr with respect to t is equal to t over ma bracket y r plus 1 minus 2yr plus y r minus 1. In a given normal mode, all masses oscillated with the same mode frequency omega, so all yr has same time dependence. As we can see in figure above, it is shown that A1 and A2 are in antiphase, The transverse displacement YR also depend upon the values of R, which is the position of the R mass on the string. So we can say that YR is the function of two independent variables, which is the time t and the location of the R mass on the string X. So we can say that Y is a function of both X and t. The partial derivative of y with respect of t in the function of x and t will express variation with time while x is kept constant. Meanwhile, partial derivative of y with respect to t in the function of x and t will express as variation with x while time is kept constant. Y is evaluated at x is equal to xr, and now as a is delta x approaching 0, we may write the sequence of xr is equal to x as r plus 1 and so on, which is we can write it as x plus delta x. And the function of y, we can write that y the function of x plus delta x and t. Using a Taylor series expansion to express the function of y in terms of y plus delta x and t, in terms of partial of y with respect to x, is described as y in the function of x plus minus delta x and t is equal to yx plus minus delta x partial derivative of y with respect of x plus 1 over 2 plus minus delta x squared multiplied by second order of derivative partial derivative y with respect of x. When substitute this equation to the first equation, which is the equation of motion for the earth mass, we can get that partial second order of partial derivative y with respect to t is equal to t over m delta x squared over delta x multiplied by second order of partial derivative y with respect of x is equal to t over m partial t over m delta x multiplied by partial second order of partial derivative y with respect to t. And here we can see that m is equal to rho delta x, so we can replace m here with rho. We get that second order of partial derivative y with respect to t is equal to t over rho multiplied by second order of partial derivative y with respect to x. This is what we call the wave equation, where t over rho is the dimension of the square of a velocity, c squared.
So now we continue with the example of problem. So the problem is, the figure shows a system of masses in the x and y plane. The masses up to m is connected with the immobile wall by the spring constant k, and the mass of m were attached with a wall with the spring constant k. So they are coupled to each other with the elastic band of the length L and under the tension 2kL. So the masses are constrained to move in the x direction only, and at equilibrium, the masses have the same x position and the springs are uncompressed. There is no friction or gravity. The displacement from equilibrium are small enough, x1 and x2 is smaller than L, so that the tension in the band stays constant. So first one, we have to describe the displacement of the masses in equilibrium, so x1 and x2. So in this question, we use Newton's law. So Newton's law, 2mx double dot 1 equal to negative 2kx 1 minus t sine theta, and we substitute sine theta as x1 minus x2 over L, so that we get 2mx double dot 1 equal to negative 2k minus t over L x1 plus t over L x2. So that we solve them, divide them with 2m, and we get x double dot 1 equal to negative 2k over m x1 plus k over m x2. So for the x2, we use the same way, we use the Newton's law, but we have the different mass and different constant strain. So be careful. So we get x double dot 2 equal to 2k over m x1 minus 3k over m x2. So for the k over m is equal to omega naught square. So we substitute them as x double dot 1 equal to negative 2 omega naught square x1 plus omega naught square x2, and it is the same goes with the x double dot 2. So for the second question is to find the normal mode frequency of the system. So to find the normal mode frequency, we have to use the matrix form. So we write the equation of motion that we get before into the matrix form. So we get it like this, and we solve them. At last, we get the equation for omega naught square minus omega 2 in bracket omega naught 2 minus omega 2 in bracket equals to 0. So we get the frequency omega 1 is equal to omega naught. It is equal to square root k over m. And that is same goes with the omega 2 equal to 2 omega naught. So it is equal to 2 square root k over m.
So we proceed to the example of the problem that related to the third subtopic in this chapter. In this problem, there are two springs hanging to each other with two equal masses. The equal masses in the figure oscillate in the vertical direction. The question is, show that the frequencies of the normal mode of oscillation are given by omega square is equal to, in bracket, 3 plus minus the square root of 5 times s over 2m. And that in this lower mode, the ratio of amplitude of the upper mass to that of the lower mass is half of, in bracket, the square root of 5 minus 1. Whilst in the faster mode, this ratio is negative half, in bracket, the square root of 5 plus 1. So theoretically, in this topic, we can know any description of the motion by do matrix method and follow step by step until we get the frequency of normal mode. But in this problem, the description of motion and also the frequency of normal mode of the oscillation are already given. So we need to show that the frequencies of the normal mode of oscillations are as given. If the upper mass oscillates with a displacement of x and the lower mass oscillate with a displacement of y, the equation of motion of the two masses are given by Newton's second law as mx double dots is equal to x in bracket y minus x minus sx, and also my double dot is equal to x in bracket x minus y. From these two equations, we bring all from right hand side to the left hand side. So the equation will equal to 0 at the right hand side. Then we take these two equations as formula 1. Next, supposedly the system starts from rest and oscillates in only one of its normal modes of frequency. We may assume the solutions as x equals to a times exponential I omega t, and also y equals to b times exponential I omega t, where a and b are the displacement amplitude of x and y at frequency w. So we note these equations as formula 2. Using this solution, we insert formula 2 in formula 1. So the new equations of motion will become like this. Then, the next step in this method, we divide the equation by m times exponential I omega t and rewrite it in matrix form like this. In this form of matrix, has a non-zero solution if and only if the determinant of the matrix is 0. So with the formula of determinant, which is AD minus BC is equal to 0, then we arrange the equation as solved for omega squared. Omega squared is equal to, in bracket, 3 plus minus the square root of 5 times s over 2m. Thus, we will get the same solution as the given by the problem. In the slower mode, we can take the positive value. So we can substitute the value in the previous matrix form and we will get the square root of 5 minus 1 over 2, which is the ratio of the amplitude of the upper mass to that of the lower mass. And also, similarly in the faster mode, we can take the negative value of the frequencies and substitute it in the matrix form. So we will get the value which is negative the square root of 5 plus 1 over 2. So, we had proven that the given frequencies of the normal mode of oscillations are true, which are omega squared is equal to in bracket 3 plus minus square root of 5 times s over 2m.
I will discuss about the problem that related to the coupler oscillation of a loaded string. So in this problem, let us consider the case when the number of masses on the loaded string of this chapter is n equal to 3. So use the equation 4.15 to show that the normal mode of frequencies are given by those three normal mode of frequencies, and repeat the problem using equation 4.14 with the normal frequency and natural frequency in the matrix method where the eigenvector components are AR minus 1, AR and AR plus 1. So I just stated that what is equation 4.15 and what is equation 4.14. So then show that the relative displacement of the masses in the mode of the problem are equal to those, and show by this sketching the relative displacement. First part that I've been highlighted there is use equation 4.15 to show that the normal mode frequencies. Okay, this is the equation of 4.15. Okay, let's see the solution. Okay, we know that the n is equal to 3 and we need to use the equations. So we're just going to substitute the n equal to 3 and also J1, J2 and J3 into the equation. So by simply substitution that value, we will get and prove the normal mode frequency. The highlighted point is repeat the problem using equation 4.114 in the matrix method there. Okay, so using the equation 4.14 there. So let's see the solutions. Okay, actually it is as the same method as before, which is n equal to 3, and we know that the fits of when n equal to 3, the fits and string, the first fits and string is A0 and the last fits and string is A4. So that's amplitude is equal to 0. So we're just going to substitute that R1, R2 and R3 into the fundamental equations, which is equation 4.14. Okay, so after that, after substitute the R1, R2 and R3, we're going to form it into the matrix format, which is there. I showed that by the arrow there, and then we're going to get the determinant of the matrix, and this is equal to 0, which is we just solve the determinant, and by that we can get the solutions for the angular frequency by solving the determinant there. So we get proving that the angular frequency equal to those three solutions. Show that the relative displacement of the masses in the modes of the problem are those three, and also show by sketching the relative displacements. Okay, as we know that we have proved the natural mode frequency, the three value, which is the first one, we have proved that equal to 2 angular frequency naught to the power of 2. So we're just going to substitute the frequencies into the equations that we also have derived before, which is R1 and R2 and R3, using the fundamental equations in the slide before. So we're just going to substitute that. So for the first one, I substitute the value for the frequency into the equations of R1 and R2. So for the second one, I substitute the equations equal into the R1 and also R3. For the third one, also substitutes in the method of substitutions. So that when we substitute all those value, we will get the relative displacement, which is for the first one, I get 1, 0, negative 1, second 1, radical to 1, and the third one is 1, negative radical to 1. So when we want to show in the relative displacement of the three masses, okay, so for the first, in the middle one, which is I got 1, 0, negative 1, it is actually in the middle the A2, which is the middle mass, the amplitude is 0. There is no amplitude there. And A1 and A3, it is actually opposite in direction. So A1 upward and A2 is downward. Okay. For the second one, which is the left hand side, it is stated that 1 radical 2 and 1, which is it is actually in the same directions, and but the middle mass is more higher displacement. And then for the third one, which is the right hand side, it is 1, a negative 2, a radical, and 1. So it is the middle one has the higher amplitude but downward, and the first and the third mass is the same direction and also have the same amplitude.
Problem 4 shows that y equal exponential I omega t multiplied by exponential of I kx satisfies the wave equation if omega is equal to ck. Okay, firstly, we simplify the equation, which we got y is equal to exponential I bracket omega t plus kx. Then we look for both second order of partial derivative y with respect to t and x. Okay, second order of partial derivative of y with respect to t, we got that it is equal to negative omega squared y. And then for partial derivative of y with respect to t, we got that the second order of partial y with respect to t is equal to negative k squared y. And then we compare the equation that we got with the wave equation, and then we got that negative omega squared y is equal to c squared multiplied by negative k squared y. When we simplify the equation, we got that omega is equal to ck, which will fulfill the requirement of the equation, and so it is proven that y is equal to y equal to exponential I omega t multiplied by exponential of I kx satisfy the wave equation.